This pen is cheap enough to lose without thinking, yet its 1 mm ball must be fitted into the tip at micron scale. Too tight, it cannot turn. Too loose, ink can flood the page. The same gap must keep the ball trapped, let it rotate, and meter a clean line of ink. Inventors struggled with it for more than half a century. And when ballpoints finally became a consumer sensation, thousands were returned. The ball does not simply open a hole and allow ink to fall through. It behaves more like a printing roller, small enough to disappear inside the tip. The surface facing the cartridge picks up ink. As the pen moves across paper, friction turns the ball inside its socket. The ink-coated surface rotates outward, touches the paper, and leaves behind a thin film. That surface then rolls back inside to collect more ink. The ball is therefore the writing point, the ink carrier, and part of the flow control system. It helps expose ink only at the place where the pen touches paper. But the ball cannot perform any of those jobs alone. Its diameter, the geometry of the socket, the clearance between them, and the behavior of the ink all affect one another. Capillary effects help move and retain liquid inside the narrow spaces, but they are only part of the mechanism. Gravity, viscosity, surface tension, writing pressure, ball rotation, and even the texture of the paper influence the final line. That is why a pen can still contain ink and refuse to write. The ball may not be rotating freely. Dried material may be obstructing the interface. The ink may no longer reach the contact zone consistently, or a tiny geometric defect may be disrupting a system that only works inside a narrow operating range. For most of writing history, every pen confronted some version of this problem. Dip pens carried only a small amount of ink and had to be replenished repeatedly. Fountain pens moved the reservoir inside the body, but still needed a feed and nib to regulate the liquid. The ballpoint proposed something different. Replace the exposed split nib with a rotating sphere. The idea appeared in a United States patent granted to John J. Loud in 1888. Loud described a reservoir instrument with a revolving marking sphere. But he was not primarily trying to improve handwriting on notebook paper. His patent discussed rough surfaces such as wood and coarse wrapping paper, where conventional pens struggled. The design could leave a mark on those materials, but it was too coarse for comfortable everyday writing. A ball capable of marking leather or wood did not automatically produce a clean, controlled line on paper. Loud had demonstrated that a sphere could carry ink. He had not solved the relationship among the sphere, the socket, the ink, and the writing surface. That missing relationship became clearer decades later to Laszlo Biro, a Hungarian journalist. Biro noticed an important contrast between newspaper printing and writing with a fountain pen. Printing ink dried quickly on newsprint and resisted smearing. Fountain pen ink behaved differently because it had to travel through a narrow feed and nib. Simply filling a fountain pen with thick printing ink would not work. The liquid could not move through the existing delivery system correctly. If the ink changed, the mechanism had to change with it. Biro began developing a pen that used a rotating ball to handle a thicker, faster-drying ink. His brother Gheorghe was a chemist, and that collaboration was crucial. A better sphere would accomplish nothing if the ink could not move around it. A better ink would fail if the socket locked the ball or allowed too much liquid to escape. The breakthrough was not the ball alone. It was the decision to engineer the ball and the ink as one system. That work continued during one of Europe's darkest periods. Biro came from a Jewish Hungarian family. By the late 1930s, Hungary's government was imposing anti-Semitic restrictions while moving closer to Nazi Germany. Biro and his family left Hungary at the end of 1938 and went to France. They could not remain there safely for long. German forces occupied France in 1940, and Biro eventually continued to Argentina. Far from Budapest, he, Gheorghe, and their business partner, Juan Jorge Main, kept refining the pen that became known as the Birome. A new patent application followed in 1943. Argentina gave Biro somewhere to continue the work. It did not give manufacturers an immediate way to reproduce the mechanism cheaply or reliably. A prototype only needs to work once. A mass-produced pen must work after thousands of balls, tips, and reservoirs have passed through separate machines. Every combination must remain inside the same narrow operating range. The distinction would soon become painfully visible in New York. American entrepreneur Milton Reynolds had encountered Biro's pen during a trip to Argentina and immediately recognized its commercial potential. But companies, including Eversharp and Eberhard Faber, had already obtained rights to bring the Biro design to the North American market. Reynolds did not wait for them. He returned to the United States and developed a modified version intended to avoid those patent claims. Legal efforts to stop him failed. and Reynolds rushed his pen into stores ahead of the licensed competitors. He did not beat them by producing a more reliable mechanism. He beat them by moving faster. On October 29, 1945, the Reynolds rocket went on sale at Gimbel's department store in New York. It cost $12.50, an extraordinary price for a pen at the time, and was promoted like a miraculous device from the atomic age. Demand was immediate. Customers crowded the store, and approximately 30,000 pens were sold during the first week. The ballpoint appeared to have gone from obscure invention to consumer phenomenon almost overnight. Then the failures began to surface. Some pens skipped, leaked, smudged, or stopped working. By the following April, approximately 6,000 of every 100,000 Reynolds pens sold through Gimbel's had reportedly been returned as defective. The public had not rejected the ballpoint principle. People clearly wanted a pen that carried its own ink, dried quickly, and did not depend on a delicate fountain pen nib. What they rejected was inconsistency. The ballpoint had become famous before it had become reliable. Failure reveals what a modern pen factory is actually manufacturing. It is not merely producing a ball, a metal tip, and a tube of ink. It is manufacturing the relationship between them. A ball can pass its own dimensional inspection and still lock inside a poorly formed socket. A socket can have the intended shape and still leak when paired with ink that is too fluid. A good ink formula can still skip if contamination reaches the tip. The individual parts may all appear acceptable while the assembled system fails on paper. The smallest component is the best place to see how demanding that relationship becomes. Manufacturing methods vary among brands and pen types, but the BIC Cristal provides a well-documented example. Its writing ball is made from tungsten carbide and is approximately 1 millimeter in diameter. Tungsten carbide is extremely hard and resistant to wear. Matters because the ball repeatedly rolls against both its metal seat and the fibers of paper. If its surface wears unevenly or its geometry changes, the clearance controlling the ink may change with it. In a typical manufacturing route, tungsten carbide powder is formed and hardened before being ground and polished into a sphere. The objective is not merely to make something that looks round. Surface variations, too small to see, may affect how the ball rotates, how ink coats it, and how consistently that coating reaches the paper. According to BIC, every ball used for the Cristal is checked for roundness and resistance. Is the first major reversal inside the factory. The part that most users never notice is the part that cannot be treated as merely close enough. A 1 millimeter sphere must remain stable through a line that may eventually extend for kilometers. Once the ball exists, the factory must trap it without destroying its ability to move. For the Cristal, the ball sits inside a brass tip. The precise sequence differs among manufacturers, but the underlying problem remains the same. Metal is formed or machined to create the exterior tip, the internal ink passages, and the seat supporting the ball. The ball is placed into the open end. Metal around the mouth of the socket is then shaped inward to retain it. Too little deformation, and the ball may not be held securely. Too much, and the socket squeezes it until it drags or locks. The tip must expose enough of the sphere to touch paper, while retaining enough of it to prevent escape. BIC describes the Cristal ball as being inserted to the nearest micron. Does not mean there is one universal 1 micron gap. It means the fit is being controlled at a microscopic scale. And there is no single magic clearance for every ballpoint pen. The correct geometry changes with ball diameter, ink properties, socket design, and the way the ball moves under writing pressure. Patented pen tip designs document clearances or ball movements in the range of only a few microns. One design describes tolerances of roughly 5 to 5 microns. Another requires more than 3 microns of longitudinal ball movement to keep its ink passage open. Those numbers are not specifications for every BIC Cristal. They reveal the scale of the problem. A human hair may be tens of microns wide. In some pen tip designs, the movement controlling the line is only a small fraction of that. The clearance allowing the ball to rotate is also the route the ink must follow. This is where chemistry returns to the story. Ballpoint ink is not simply colored water. Exact formulas are proprietary and vary by manufacturer, color, and pen type. Conventional ballpoint inks commonly combine solvents, resins, colorants, and additives that influence flow, drying, adhesion, friction, and wear. The ink must move far enough to reach and coat the inner surface of the ball. It must form a reasonably consistent film as the sphere rotates. Then it must transfer onto paper and dry quickly enough to resist smearing. At the same time, it cannot behave like water pouring through an open tube. If the ink flows too easily, the tip may create heavy lines, blobs, or leaks. If it resists movement too strongly, the pen may feel scratchy. require excessive pressure, or stop writing while ink remains inside the cartridge. Ink also functions within the frictional system. It helps lubricate the contact between the ball and its seat. Changing the solvent, resin, or friction-modifying additives can affect not only the appearance of the line, but also writing smoothness and long-term wear. The factory is therefore not searching for the thinnest ink or the thickest ink. It is searching for ink whose behavior matches a particular ball and socket. Once mixed, the ink must be filtered and checked before filling. A particle that appears insignificant inside a mixing vessel can be enormous relative to a clearance measured in microns. The rest of the crystal looks almost plain by comparison. That apparent simplicity is deliberate. Plastic is heated and shaped into the barrel and other components, using extrusion or injection molding depending on the part. Cooling stabilizes each shape before the components are released, inspected, and directed toward assembly. But these visible parts are not merely cheap shells around the real technology. Each one removes another possible inconvenience or failure. The crystal's hexagonal barrel recalls the shape of a pencil. It creates stable contact points for the fingers and prevents the pen from rolling as easily across a desk. Its transparent polystyrene body protects the cartridge while allowing the user to see the ink level. A small hole in the barrel helps balance the pressure inside and outside the pen. As ink is consumed, air and pressure conditions must remain compatible with continued delivery. The cap is colored to match the ink, allowing users to identify the color without testing the pen. It protects the writing tip and includes a clip that can hold the pen to a pocket or notebook. Modern versions also contain a feature unrelated to ink flow, a ventilated cap. International safety standards for writing instruments specify cap designs intended to reduce the risk of asphyxiation if a cap is inhaled and becomes lodged in the airway. The opening cannot guarantee safety, but it may allow airflow while medical help is sought. That hole is a reminder of what happens when an industrial product becomes universal. Once pens reached schools, homes, and offices, their design had to address risks far beyond the act of writing. Now, all these components must converge without ruining the microscopic interface. Ink is mixed, filtered, and checked for the properties required by the product. Empty cartridges are positioned for controlled filling. The metal tips are installed. The rear of the ink system is sealed or managed according to the cartridge design. The filled cartridge is inserted into the barrel, followed by the plug, cap, and remaining components. This stage looks simpler than manufacturing the ball, but it can still destroy everything that came before it. A bubble can interrupt delivery. A particle can reach the socket. Incorrect filling can change performance. A poorly installed tip can disturb alignment. A sealing problem can expose ink to air or allow it to move where it should not. At the end of assembly, the pen looks finished. That appearance proves almost nothing. The real verdict appears only when the ball touches paper. Quality programs vary by factory and product, and manufacturers do not write every pen dry before selling it. Instead, they combine process monitoring, dimensional inspection, automatic controls, and sample-based performance testing. Beek says the crystal passes through more than 70 controls during manufacturing. These may cover materials, dimensions, ink behavior, assembly, starting performance, line continuity, leakage, and endurance. In a writing test, a machine holds the pen against a moving surface under controlled conditions. The tip draws repeated patterns while the line is examined for skipping, variation, excess ink, or premature failure. The machine is not merely checking whether the cartridge contains ink. A continuous line means the ball is rotating. The socket is retaining it without locking it. Ink is reaching the contact zone. The film is transferring onto paper. The cartridge is delivering material without a serious interruption. The tip is aligned, and the complete interface is surviving friction. Then the scale changes. BIC says a crystal can write for up to 3 kilometers. The exact result depends on the model, writing conditions, and test method, but the contrast remains remarkable. A ball only about 1 millimeter wide can keep the same interface functioning across kilometers of line. Il also lists 7,250 kilometers as the total length of writing tests carried out on batches of its ballpoint, gel, and roller pens. Is not the distance written by a single crystal, nor is it a figure exclusive to this model. It demonstrates the scale involved in validating writing instruments through repeated testing. The test line finally closes the mystery hidden inside the title. There was never one universal impossible gap. There was a narrow operating range that had to be matched to a particular ball, socket, and ink, and then reproduced at industrial scale. The ball stayed trapped. The ink stayed controlled. Yet both remained free to move. This is the point where precision becomes reliability. But reliability alone did not make the ballpoint universal. It still had to become affordable. After the post-war ballpoint craze exposed the limitations of products rushed to market, Marcel Bitch and his partner Édouard Buffard pursued a different strategy in France. Their company already manufactured parts for writing instruments. Bitch recognized that the ballpoint could reach a mass market only if its fit, ink, and manufacturing consistency improved while its price fell. BIC's own history emphasizes the use of skills associated with Swiss watchmaking to refine the fit between the ball and the ink tube. Rather than treating the ballpoint as a novelty capable of commanding a luxury price, the company designed it for repeatable high-volume production. The BIC Cristal left the factory in Clichy in December 1950. Its success did not come from adding springs, decorative mechanisms, or expensive materials. It came from removing what was unnecessary while tightening control over the few relationships that mattered. According to BIC, approximately 10,000 crystal pens were sold each day during the first year. The company says several million are sold daily today. BIG did not produce the first revolving ball patent, and it did not originate Biro's central ink and ball insight. Its industrial achievement was turning an invention that could work into a manufacturing system that could work again and again. Distinction is easy to overlook because the final product is so inexpensive. For much of writing history, a good pen was an object worth maintaining. It might be refilled, repaired, carried for years, or given as a personal possession. Mass-produced ballpoints changed that relationship. Reliability became cheap enough to purchase without much thought, and eventually cheap enough to discard without much thought. Not every ballpoint is disposable. Refillable designs exist, materials vary, and actual recycling possibilities depend on both product construction and local collection systems. But a small object combining plastic, metal, and residual ink illustrates a strange contradiction. The precision inside a product may be far greater than the value people assign to it after purchase. Now return to the line drawn at the beginning. Inside it is a patent that worked on rough material but failed as an everyday pen. An ink problem recognized by a journalist and investigated with his chemist brother. A design carried through persecution and exile. A patent race that rewarded speed before reliability. A consumer craze that sold thousands of expensive pens before factories had mastered consistency. Inside that same line is a tungsten carbide ball about 1 millimeter wide. A brass socket shaped tightly enough to retain it and loosely enough to release its motion. An ink formulated to move through a space measured in microns, and a testing system that proves the relationship across kilometers of friction. The pen looks simple not because there is nothing inside it, but because all of its difficulty has been hidden inside a gap the writer never sees.